Hello everyone, and welcome back to Algebra 1 with Miss Betsy. Today we are going to be talking about factoring and using prime numbers. If you wish to follow along with the text that I am referencing in this video, you'll want to have the second edition of Algebra 1 for Christian Schools. It's published by Bob Jones University Press. Third edition does not work to track directly with this video, but you can still learn lots of things about factoring and about how to use prime numbers regardless of what edition you have. If you are following with me, I am in section 1.8 and it's entitled Factoring and Prime Numbers, and we're going to begin on page 31. But let's go ahead and pray first and then we'll get started. Father God, I thank you for your goodness to us, and I thank you for the beauty of the world around us. I thank you for the privilege of being able to get up in the morning and see the sunrise and to hear the song of the birds that you created in the air. Father, I ask that you would help us to learn these concepts of how to work with factoring and with prime numbers, and that we'd be able to continue to make progress in studying this topic of Algebra 1. Father, I ask that you be with us today, and I thank you for that in Jesus' name. Okay, I thought today would be a good day for the lame joke to be math related. Can you tell me what it is that 0 said to 8? So what did 0 say to 8? You know, here's our thought bubble. And let me go ahead and use black or something else here so you can actually see it. Here's 0, runs up against 8, and what does he say? He says, nice belt. So, there's your lame joke for the day, even tied right into math. So, we have been spending time talking about integers, and we know that integers are, I'm going to call them I'm going to call them whole numbers. There's technical definition again, but it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, plus the negative numbers. So we're not dealing with 1.5, we're not dealing with negative 7.3, we're not dealing with pi yet. We're just simply dealing with what you, in a non-technical math way, might think of just whole numbers. And we have learned in the past and earlier this year in our beginning sections of chapter 1 that factors, we've been reminded that when you multiply two numbers together to get an answer, that the numbers that you multiply together are called factors. So if we have 2 times 4 is equal to 8, the integers 2 and 4 are factors of 8, and 8 is the product. Now, how many ways can you multiply factors together that will give us a product of 8? Well, you could say 2 times 4. You could say 1 times 8 is 8. What else could you do? Now, we could also say 2 times 2 times 2 is 8, but we want to have only a pair of factors. So we have 2 times 4 is 8, 1 times 8 is 8. There's 2 other ways we can do this, and you might not naturally think of this, but isn't it true that if you take 2 negatives together, you multiply them together, and you get a positive? We studied this just last lesson. And we could also say negative 1 times negative 8 is equal to a positive 8 as well. So if I asked you to write all of the factors of 8, it would look something like this. You would say it was plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. If I asked you to give me all of the factors of 8, this is what it would look like. Now, someone out there might be thinking, well, let me see. If instead of having 8, I asked you to give me the factors of 3, What are the factors of 3? I guess I'll finish writing that 3. Factors of 3. Well, you can say 1 times 3 is 3. And you can also say -1 times -3 is 3. And couldn't you also say that 2 times 1½ is 3? 2 times 1.5 is 3. Yes, you can. These are definitely true statements, but when we're factoring, we're not going to use partial whole numbers. You can only use integers as your factors. So when I ask you to give me factors, I'm not going to have any fractions in there. I'm not going to have any decimal numbers in there. What we're going to talk about today, though, are what we call prime numbers, and we're going to use only prime numbers to give us the factors of whatever integer we come up with. So what are prime numbers? This is something that you must know. Prime numbers are integers. First of all, they can't have fractions or decimal portions. Integers, and they have to be greater than 1. So not only are they cannot be negative numbers, they cannot be 0 either. 0 and 1 are not considered prime numbers. Prime numbers are integers greater than 1 whose only factors are the number 1 and that same number itself. And I just used the number 3 to illustrate that while it's true that 2 times 1½ is equal to 3, 2 and 1½ are not factors of 3. The only way you can come up with 3 is to say 1 times 3. Also -1 times -3, but with prime numbers we're talking about positive numbers. 3 is a prime number. The only way that you can multiply two positive numbers together and end up with 3 is to say 1 times 3. What's another one? 5. The only way you can get 5 is to say 1 times 5. What about 6? Well, you can say 1 times 6, but you can also say 2 times 3. So 6 is not prime. What's the next one? 7. Looks like we've got a pattern going here, don't we? We have odd numbers. 3 is 1 times 3, 5, 1 times 5, 7, 1 times 7. Are we seeing a pattern here that says all of our odd numbers are going to be prime numbers? Isn't it true that 9 is equal to 1 times 9? Yeah, that's true. However, 9 is also equal to 3 times 3. So 9 is not a prime number. Our first 3 prime numbers here, actually we have 2 as well. 2 is 1 times 2, correct? What about 1? Why didn't I do 1? 1 is equal to 1 times 1. Our definition says that the integers have to be greater than 1. So our first 4 prime numbers, 2, 3, 5, and 7. Now, we saw that 6 wasn't a prime number because you could say it was 2 times 3. And we saw that 9 also was not a prime number because that could be expressed, it could be factored as 9 times 9. So if those are not prime numbers, what are we going to call those? Well, they also have a number, and it's composite. And these are called composite numbers. Now if you have composition flooring, it's something that is not solid wood. It's a combination of different materials. And I think that's probably where the composite number comes from, because composite numbers have factors, can be factored in ways other than just using prime numbers. So they're non-prime numbers greater than 1 again. You can almost think of it as the composite numbers are everything else. Either a number is going to be not prime. If it's not prime, it's a composite number, except for the two special cases, 0 and 1, by definition, are neither prime nor composite. So you have a way that you can break integers up, 3 definitions. The numbers are either going to be composite numbers, they're going to be prime numbers, which means they can only be factored as with the 2 integers 1 and that number itself, or they're going to be 0 and 1. 0 and 1 are the special cases, and they're not prime, they're not composite, they just are. So now that we have those definitions down, we are going to see that every single number that's out there can be factored in a way where the factors of that number are uniquely prime numbers. What I mean by that is that every single number that you're using in there, that we're saying 2 times 3 times 5 times 11, those are all prime numbers. We're going to see that we can come up with a special way of multiplying integers together to arrive at a number, and that's what we call the prime factorization. But before I tell you about that, let's list some of these prime numbers, and these are things that you're going to want to memorize. Because in order to prime factor, you need to know what numbers are prime and what aren't. Know these prime numbers. As you work with prime factoring, it's going to be second nature to you. You'll know what they are, but if you have not memorized these already in another class or at home up to this point, just need to know that the first groupings of prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 21. Is 21 prime? Nope. Remember your math facts? 3 times 7 is 21. Do you see the pattern that even I fell into? 17, 19, 21. It's not, all of these numbers here are odd, but it's not every single odd number is prime. We have 23, 29, 31. Now, if you learn up to about 31, even just up to 29, it's going to make your job easier. Let's look at this. 2 is only 1 times 2, 3. We can't have 4, 2 times 4. We can't have 6, 2 times 3. Can't have 8, 2 times 4. Can't have 9, 3 times 3. Can't have 10. 2 times 5 is 10. Are you noticing there is a pattern here? We have 2 at the beginning as a prime number, but every single other number here is odd. There's nothing else that's an even number. And the reason for that is no even number other than 2 can be prime, because any number that's even, how about 122? I don't know if that's prime or not. Actually, I think it is. Not exactly prime. You'll see what I mean at the next step. Any number you learned that's even, you can divide it by 2. So 122 can be factored, can have a factor of 2. So any even number other than 2 cannot be prime. And this is what I meant when I said actually 122's prime. It's not, obviously, because it's an even number. But that great big number right there, 61, is a prime number. Okay? Don't expect you to know that. I do, however, want you to memorize these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll give you a gift here. Memorize know these 10 prime numbers. It will make your life a whole lot easier. It takes no time at all just to learn them. You can figure them out each time, but why would you want to sit here and think, okay, 8 and 18, 20. Okay, 20's not, it's even. 21 is 3 times 7. Sometimes just memorizing a list of numbers is a good thing. Now, let's talk about prime factorization. When we do prime factorization of a number, every factor has to be a prime number. Prime factorization. This means all the factors are prime numbers. Not only are they must be prime. So, let's go back to 8. I've referred to that very briefly and then talked about it at the beginning. How can we factor 8? We can and not using the negatives, but we can factor and say that 8 is equal to 1 times 8. 8 is also equal to 2 times 4. But this is not the prime factorization. Neither of these ways of factoring 8 is the prime factorization because 8 is not a prime number and 4 is not a prime number. So, what other way is there that we can do this? Well, what if we said, I can't factor 2 any other way than just saying 2 times 1. However, I can say that 4 is equal to 2 times 2. So rather than saying 2 times 4 or 1 times 8, if I say 2 times 2 is 4, times 2 is 8, I have come up with a way of factoring 8. It's factored because it's written as a combination of factors that multiplied together give us this 8, where the only factors that are in here are prime numbers. And in this case, it is a single, unique prime number that is used as a factor 3 times. I'm using this exponential notation that you learned about, or that you reviewed in section 1.7. So either of these ways here would be legitimate expressions of the prime factorization of 8. 8 is equal to 2 times 2 times 2. You use that shorthand method of exponential notation where you say, or 8 is equal to 2 cubed. Because what 2 cubed means is that 2 is used as a factor 3 times. Let's go ahead and look at some examples in your book. I said we started on page 31. I think I'm on page 32 now. Example number 1 asks us to find the prime factorization of 12. Example 1. Find the prime factors of 12. And they're going to use something that they call a factor tree. You can call it a stem and leaf plot. What you do is you start with 12 and you think, okay, how can I come up with 2 factors? What are 2 factors? 2 things that I can multiply together that equal 12. Well, 2 times 6 is equal to 12. But we're looking for prime factors. Is 2 a prime number? Yes. Is 6 a prime number? No, 6 isn't. You can come up with 2 numbers that multiplied together are equal to 6. Is 2 prime? Yes. Is this 2 prime? Of course. And is 3 prime? What I'm going to call the stem and leaf plot here, I'm going to just circle these. Once you get to the end of a branch, if you will, circle your numbers that are prime. 12 is equal to 2 times 2 times 3. 2 times 2 is 4, times 3 is 12. Well, I said that 12 started off breaking this apart with my factor tree by saying it was 2 times 6. Can't I also say 3 times 4 is also a way to come up with 2 factors multiplied together is 12, correct? Is it going to work? Well, is 3 prime? Yes. Is 4 prime? No, it's not. But you can say that 4 is equal to 2 times 2. Look at the end of each of these branches. See that they're all prime numbers. You can say that 12 is equal to 3 times 2 times 2, right? 3 times 2 is 6. 6 times 2 is 12. Now, in your book, you're going to see some places where they might do your factorization like this, but something that is always going to help you is to keep things in alphabetical order when they're variables. If you have A, B, C, or A, B, D, and Z, it makes more sense. Our brains are wired to think you start at A and you go towards Z. Our minds are also wired when we consider numbers to think in increasing order. You start 1, 2, 3. So if you rewrite this with your lowest numbers first, which you're totally allowed to do because of the commutative property of multiplication, 2 times 2 times 3, which of course is exactly the same collection of factors that we used when we multiplied it, when we used our factor tree to come up with prime factors the first time. So what is the prime factorization of 12? What's 2 times 2 times 3? Every single number here is prime. If you want to write this as using exponential notation, what's it going to be? You have 2 used as a factor. How many times? Twice. Times 3 used as a factor. How many times? Only 1 time. 3 to the first. But we don't write that little 1 because we know that 3 by itself is already used one time. So 12 is equal to 2 squared times 3. And this is what we're going to call the prime factorization. And with the larger numbers, there will be several different ways that you can break the number apart as you're progressively factoring it. But as I've illustrated here just with this simple problem, you're still going to end up with the same factorization because there's only one possible way to prime factor every single number. Example 2 asks us to find 3 factors of 36. This is example 2. Find 3 factors of 36. In your book, they begin with a different breakdown than I'm going to. So let me explain what I'm doing here. I think 36 what jumps into my mind first is that 36 is equal to 2 times 18. True? 2 times 18 is 36. Is 2 prime? Yes. Is 18 a prime number, or can you think of another pair of factors that equal 18? Well, I can. I have 2 times 9. I also could have said 3 times 6, couldn't I? But I said 2 times 9 is 18. 2 is prime, 9 is not. Because 9 can be factored into 3 times 3. So, if we're supposed to find 3, let me see, 3, what's it saying? It says factor 36 into primes 3 ways, I think is actually what your book says. Factor 36 into primes 3 ways, because we've said there's only one possible combination of prime factors for every number. That's what they call a unique factorization. Here's one way that we arrived at it. First we said 36 was 2 times 18. I could also say 36 would be 3 times 12 gives me 36. 3 is prime. 12 can be divided into 2 times 6. 2 is prime. 6 is not. I could also have said 12 was 3 times 4. 6 is 2 times 3. And again, I've circled the end of all of these little stems here once we got to the point where they were prime numbers. What's another way that I could factor 36 into primes? Well, you have your multiplication factor fact that says 4 times 9 is 36. 4 is not prime because 2 times 2 is equal to 4. 2 is prime both times. I'm going to circle those, and 9 is 3 times 3. I have prime factored 36 3 separate ways. Now, if what I have said is true, that there's one unique way, one unique combination of prime factors, we need to be getting the same answer here every time, don't we? 36 is equal to 2 times 2 times 3 times 3. I've used that one, I've used that factor, I've used that factor, and I've used that factor. The circled endings are all a part of your prime factorization. 2 times 2 times 3 times 3. In exponential notation, that would be 2 squared times 3 squared. 4 times 9 is 36. Well, what do I have over here? I have that 36 is equal to, and I'm just going to start up here at the top and write the factors as they come. 3 times 2 times 2 times 3. 3 times 2 times 2 times 3. Let's illustrate this, or let's write this using exponential notation with the prime numbers in increasing order. So we're going to start with a 2. It's used as a factor twice. And then we have 3, which is also used as a factor twice. 36 is equal to 2 squared times 3 squared. 36 is equal to 2 squared times 3 squared. Over here, this is laid out very nicely. And you see that 36, again, is equal to 2 squared times 3 squared. Your book asked you to show how you can factor 36 into primes 3 ways. If you have your book in front of you now and you look, you'll see that they have another one. They said 36 can be factored 6 times 6. 6 is not prime, but it factors as 2 times 3. Again, we have 2 times 3. All 4 of those numbers there, again, are prime. 2 is used as a factor 2 times. 3 is used as a factor 3 times. So we have actually 4 separate processes here, 4 separate ways to approach finding the prime factorization of 36. So what's the purpose of this illustration? Well, one is to say that sometimes your method is going to look different. That you choose to solve a problem is going to look different than what it does in your teacher's edition. So if you ever have a question, you say, okay, Mom, is this the same as this? Or parents, send me a text. In all likelihood, you have just come up with a different representation, a different way of approaching the problem. And here, 4 different ways. Everybody's mind doesn't think the same way. When I sat down and worked these problems in your book, as I'm prepping for this lesson, in your book, the first method that they showed was 36 is 6 times 6, and that's not what jumped into my mind first. But it doesn't matter. We can factor any prime number. Let me go ahead and do one more though. I want to go ahead and do example 3. What I'm going to try and do is work through the majority of the examples in your book so that I can explain them to you. When we do when they have skill check sections in there, I'll work some of those as well. Example 3 says prime factor 86. Example 3. Prime factor 86. So what you're going to do is set up your factor tree. 86 is an even number, isn't it? So an easy default here is anytime you've got an even number, you know that you're going to have a factor of 2 in there. 86 divided by 2 gives me 43. 2 is prime. What about 43? Well, can you divide 43 divided by 2? No. 3 times something equal to 43? No. 4 times something equal to 43? 5? 6? There are no factors other than 1 and 43 that will give you the resulting product of 43. So 43 is a prime number. So the prime factorization of 86 is not 2 times 6. The prime factorization of 86 is 2 times 43. As you're working through the problems in these sections, some of the prime numbers are going to be larger. Now, let's go ahead and look at example 4. Any number, every single number can be prime factored. Sometimes it can be very tedious to do that. Example 4 is one of those numbers that's a little bit tedious. And they ask us to factor 14,175. What am I going to do here? 14,175. It ends in 5, so I know that I can divide this big number here by 5. Do your long division. Don't use your calculator yet. I will tell you at some point that, okay guys, we're in class up to the point where I want you to use your calculator. That's going to end up being 2835. This number is not prime because it ends in 5. So we're going to divide this number by 5 again. I don't wish to do that one in my head. 2835 divided by 5. 5 times 5 is 25. 33, 6, 35, 7. 567. Now, what in the world can I divide 567 by? Well, there's some factor rules that will help you. If a number is even, you can divide it by 2. There's something, how do you figure out if you can divide a number by 3? Something they call sum of the digits. If you add up 5 plus 6 is 11, plus 7 is 18. If you have a number that when you add those digits together, you can divide that number by 3, you can divide the whole number itself by 3. So, 567 is divisible by 3. 3/8 or 24. I do not enjoy long division. 27. Is that right? 3/8 or 24. 3 times 8 is 24. 3 times 9 is 27. You know how I knew that 188 could not be the correct answer? 188 is an even number, and we can't, this number is not divisible by 2 because it's not an even number. 188 is divisible, so be doing your checking as you go on along. 189 again is divisible by 3. When you divide that by 3, you have 63, which again is divisible by 3. 63 divided by 3 is 21. Again, you can divide 21 by 3. And you have 7. Let's go back and look at this factor tree. 5 is prime, 5 is prime, 3 is prime, 3, 3, 3, and 7. We're done. There's nothing else that we can do when we're prime factoring this. So how do we write our answer? Let's start with the lowest prime number that is a factor. Lowest prime factor. We've got a 5 and a 3 and a 7. So we're going to say that 14,175 is 3. How many times is it used as a factor here? 1, 2, 3, 4. 3 used as a factor 4 times is 3 to the 4th. 5 is used as a factor twice. 5 squared. We have anything remaining? Yep, we have one factor of 7. So the prime factorization of 14,175 is 3 to the 4th times 4 squared, 3 to the 4th times 5 squared times 7. See what I mean about it being long and tedious? This right here, 3 to the 4th times 5 squared times 7 is what they call simplified exponential form. And this is really how you're going to want to indicate your answer, because it would be true that it is 3 times 3 times 3 times 3 times 5 times 5 times 7. That's true, but it's really easy to get lost in just the sheer length of that expression of the factorization here. Yes, you may. But if you use the exponential form here, it's much more concise and you're not going to get lost. Okay. Now, this is something that I want to point out to you, where I have a significant disagreement with the method of expressing things that they show you in your textbook. To me, their examples of how you use a factor tree can be really confusing to new students, to beginning students, and you're just writing a bunch of extra stuff anyway. Let me illustrate what I'm talking about. When they prime factored 36, I showed you how I prime factored it when we had 12 times 3. I said 3 is a prime number. 12, one way would be 3 times 4. 4 factors into primes as 2 times 2. Anytime I got to the end of a branch and the number was prime, I circled it. So you know that when you're at the bottom of all of your branches, once they're circled, you have completed the prime factorization on that branch of your factor tree. You have 2 squared times 3 squared. Now let me show and explain to you what they're doing here. I recommend this method. I do not recommend this. However, if this makes sense to you, please do it. We have 36 is 12 times 3, correct? Okay. 12 can be factored into 4 times 3. It's almost like they're keeping factors on the same line. 3 is already prime, so we're going to bring that down. Now, this is prime, this is prime. 4 is not prime. It factors into 2 times 2. 3 is prime, so you bring that down. 3 is prime again. And I can't draw this morning. So you drop the 3 down again. Then, all of these digits down here that are on the same bottom line together, that's the prime factorization. 36 is 2 used as a factor twice times 3 used as a factor twice. Obviously, clearly the same answer, because there is only one way that you can express any individual integer as a product of primes. The reason I think this is confusing is because you think, okay, I've got these extra 3's out here. Am I supposed to be doing something with them? To me, it's confusing. If this is a more structured, methodical approach for you, please use it. If this makes more sense, go ahead and use this where you circle the primes, you use less, you have less writing. To me, this is less confusing. I think there are some of you, however, who might like to just do this line, especially if you're using lined paper, then this line, then this line, and you just continue carrying down the prime number the whole way. Now remember that last number that we multiplied, that we found the prime factorization of, 14,175. You look at your text and you've got this ginormous amount of work that they've done because they continue bringing down the number, the prime number, even when you don't need it anymore. For those of you who are looking at the second edition of the text, this will make sense to you. Okay, last thing. We've concentrated a lot on using factor trees here. There's another way, another method of using division to prime factor, and this is called several different things. It can be called using a ladder, using successive division, or using upside down division. This is the ladder method. They also call it successive division. I don't think I spelled that right. Successive division or upside down division. Repeated division. Let me illustrate for you. We want to prime factor 18. And you're going to start with the lowest prime number that divides into the number that we're factoring. Start with lowest prime factor. Our lowest prime factor that divides into 18 is 2. Instead of our division bar like that, we're going to turn it upside down. How many times does 2 go into 18? 2 goes into 18 9 times. Will 2 go into 9 now? No. 3 divides into 9 3 times. This is the upside down division. You look at the numbers on the outside. They're all prime numbers, aren't they? Don't have to circle them here because they're all on the outside of our ladder, on the outside of our upside down division. So we have seen here that the prime factorization of 18 is 2 times 3 squared, because 3 appears on the outer part of this ladder twice. Okay? If we did this factor tree, you might say 3 times 6 is 18, 2 times 3 is 6. You have those circled, and you see that 18 is 2 times 3 squared there as well. Two different ways of approaching the problem. For example, okay, this by the way was example 5. Let's go ahead and use example 6. It says use ladder division to find the prime factorization. This is example 6, 3,780. We're going to use upside down division, ladder division. Start with the lowest prime number that will factor evenly into this. It's an even number, so we know that we can divide this by 2. So you do your division and you have 1,890. It's still an even number, so you can cut that in half again and you have 945. And you're probably jotting down some notes on the outside as you're doing the division if you can't do it in your head. Can I divide by 2 now? No. Can I divide by 3? How do I know if I can divide by 3? I'm going to add up these digits. 9 plus 4 is 13, plus 5 is 18. I can divide 18 by 3, so I can divide this entire number by 3. So it goes into 9, 315 is how I would divide 945 by 3. Can I divide this number by 3? 3 plus 1 is 4, plus 5 is 9. Yes, I can divide this by 3. 3 goes into 30 6 times, and into 15 5 times. That's not true, is it? 3 times 65 is not equal to 315. There's value in writing your division out sometimes. 3 goes into 3 once, 3, 5. 315 divided by 3 is 135. Is it? 315 divided by 3, you have 1 times 3 is 3, 0, 5. 315 divided by 3 is equal to 105. Do you see the dangers of doing too many things in your head? I talk to kids all the time and say, oh, I know what it is, I know what it is, I know what it is. Be careful with doing things in your head. I encourage you to learn just simple math computations in your head, but I'm really going to stress for a good while now that you show all of your steps. Take a little bit of extra time to do your division off to the right-hand side. Again, we can divide 105 by 3, because 1 plus 5 is 6, and you can divide 6 by 3. 3 goes into 10 3 times, so we have 35. Can you divide 35 by 3? No. Finally, we're going to move up to 5 times 7 is 35. All of our digits on the outside of our ladder are prime numbers. So we are finished. And the solution to this would be to say that 3,780 can be written as a product of primes. 2 is used twice. 3 is a factor 3 times. 5 and 7. So we have 2 squared times 3 cubed times 5 times 7. This is the prime factorization of 3,780. In our homework for this section, you're going to have some really large numbers. Just take the time to go through them. What they're trying to do, the purpose of these, is to really cement into your brain which numbers are prime and which are not prime, and to get you to understand that you just keep dividing successively downward until the only factors that you're using are prime numbers. Thanks. I'll see you next time.